Good morning, students. In this section, we are going to deal with progressive wave or traveling wave. What is meant by progressive wave or what is meant by traveling wave? It is a wave which travels from one point of the medium to the another. So, the wave which propagates from one medium to another is called progressive wave or traveling wave. So, they are all traveling wave is also known as progressive wave because they progresses from one point to another. Both longitudinal and transverse waves can be traveling wave. The wave as a whole moves along one direction. That means all the waves that we commonly draw. For example, I am drawing a wave here. This is a sine wave. Here you can see the wave is propagating forward. Here you can see the wave is propagating forward. This is a sine wave. Now, I draw another kind of wave here. This is a cos wave. Here also the wave is propagating forward. So, these kind of waves are examples for plane progressive waves, or we will say progressive harmonic waves. So, what is the difference? What is the difference between progressive wave and progressive harmonic wave? Any wave which progresses forward from one point to another is called progressive wave. It can be transverse wave, it can be longitudinal wave also. But plane progressive wave or progressive harmonic wave means when the wave is propagating through a medium, the particles vibrate simple harmonically. That means the wave which can be denoted by a sine wave or a cos wave. The particle vibrates simple harmonically. So, that can be represented by a sine wave or a cos wave. Such kind of wave is called progressive harmonic wave. Okay, that is the difference. Progressive wave means anything. Any wave which propagates forward can be a progressive wave. But when the wave progresses forward, if the particle is vibrating simple harmonically, then it is called progressive harmonic wave. So, let us see the displacement relation of a plane progressive wave. Displacement relation of a progressive harmonic wave. Suppose, imagine a simple harmonic wave is originating from a point O. So, at the time t is equal to 0, the particle is at 0 itself. Then the displacement of the particle at the origin. So, imagine the particle is starting from the origin O, and at the time t is equal to 0, the displacement of the particle at the origin can be given by the equation y 0 t, because the particle is at the origin, that is equal to a sin omega t, where a is the amplitude of the wave and omega t is called phase. Now, after a time t, the particle progresses forward. So, the displacement of the particle after a time t can be given by See what is the change I am giving to the equation. Here it was y0t is equal to a sin omega t. After a time t, the particle will have a displacement of x. Initially the particle was at the origin, that is why I put here O. After a time t, the particle had a displacement of x. Therefore, I will write the equation as y x comma t. That is equal to a sin omega t minus phi. First equation is simply a sin omega t. After a time t, it will be a sin omega t minus phi. Initial phase. Phi is the initial phase. We discussed it in the last session. So minus phi means it is lagging, because first this particle started moving. After a time t only, the particle reached here, or after a time t only, this displacement happened. That is why there is a phase difference of minus phi. Okay. There is one relation connecting phase difference and path difference. Phi is equal to 2 pi by lambda into x. X is that displacement, or x is called path difference, and phi is the phase difference. So this is the relation connecting phase difference and path difference. But 2 pi by lambda is equal to k, propagation constant. We studied in the last section. 2 pi by lambda is equal to k. Therefore, phi is equal to k into x. Hence, this equation can be written as y x t is equal to a sin omega t minus kx. Y is equal to a sin omega t minus kx. So this is the expression for plane progressive harmonic wave, the displacement relation of the plane progressive harmonic wave. So here you can make sure that the wave is propagating along the x axis and the particle is displacing along the y axis. That is the meaning of this. Wave is propagating along the x axis and particle is displacing along the y axis, because displacement of the particle is perpendicular to the direction of propagation of the wave. Okay. Now, here the wave is propagating along the positive x axis. So, I will write here now, if the wave is propagating in the negative x direction, then what will be the equation? If the wave is propagating along negative x direction, then our equation becomes y x t is equal to a sin omega t plus kx. Y is equal to a sin omega t plus kx. So you can see the difference. Here it is a negative sign, here it is a positive sign. So when positive comes in the middle, you can analyze that the wave is propagating along the negative x direction. Okay. Now, you can write the equations in other forms also. Other forms of the same equation, I can do like this: y x t is equal to a sin. Instead of omega, you can write 2 pi by capital T into small t. Omega can be written as 2 pi by capital T into small t, minus k can be written as 2 pi by lambda into x. So, equation can be written in this form also. Sometimes in the question paper they will be giving like this, sometimes they will be giving like this, and if I put a positive sign here, that means the wave is propagating along negative x axis. So, the equation can either be represented in this way or it can be represented in this way. Okay. Now, reflection of a wave, sound wave, when it strikes a medium or strikes a boundary, it will get reflected back. So, there are two ways in which the waves can be reflected. Number one, the sound wave can go hit a rigid boundary and come back. For example, here, this is the wall. When I speak, sound wave goes and hits this wall and then reflect back. That is a rigid boundary. Now, the sound can be reflected from an open boundary. Open boundary means, imagine a flute. So, we will blow from one side, the air will pass through the flute, it will reach the end of the flute, and the air outside the flute is rarer than air inside the flute. Air outside the flute will be rarer than air inside the flute. That means density of the air. Density of air outside the flute is lesser. So, the sound will go hit that rarer medium and then reflects back. That is an open boundary because sound is going hitting the air itself and coming back because of the change in the density. That is what is called reflection from open boundary. So, there are two ways the sound can be reflected. First one, reflection of sound from a closed boundary, and second one, reflection of sound from open boundary. So, just write the heading like this: reflection of a wave from a rigid boundary. When a travelling wave is reflected from a rigid boundary, it is reflected back with a phase difference of 180 degree or phase difference of pi radians. But when it is hitting a open boundary, there is no phase change. Phase change will be 0 itself. So, you can write that when a travelling wave is reflected from a rigid boundary, it is reflected back with a phase change of 180 degree. The crust is reflected back as trough. The crust is reflected back as trough. Now, give the next heading: reflection of a wave from an open boundary. When a travelling wave is reflected from an open boundary, comma, it suffers no phase change. Full stop. Here, the crust is reflected back as crust itself. Crust is reflected back as crust itself. Okay. So, that is enough for today. Thank you.